Okay, let's start today's lecture. So this is your 12 volt supply battery. This goes to a switch. This circuit goes to a electromagnet, which then connects to a mechanism which can make the contact, which can break the contact, and this is how your circuit gets completed. And here you have another piece which gets connected to the speaker or the output side of the speaker, right. So as soon as you close the switch, the current flows through here. This electromagnet gets energized, it attracts this part here. As soon as this gets attracted here, this contact breaks open. As soon as this contact breaks open, this magnet gets demagnetized or de-energized. It again goes back. There is assumed there is some spring mechanism to take it back. It again goes back. Again, once it goes back, this contact gets made. Again, there is electromagnetic energization. Again, it pulls it back. Again, it goes back. Again, it pulls it back, and just sort of create the vibration motion. It's like oscillator, but it's like some sort of electromagnetic oscillator. You can think of it that way, right? This oscillation happens at a frequency about 300 to 500 hertz. So very low frequency, 300 to 500 hertz, right? Very low frequency, but not as low as what, let's say, we can perceive it using the eyes, but still much lower. Especially now we are talking about kilohertz and megahertz of frequency, right? So some of the scooters would have this high pitch noise or high pitch this thing could be higher frequencies. Some of the other vehicles would have lower sort of sound, maybe at lower frequencies, and so on. All of this type of current, so you can imagine how would this current look like. If you see this current I drawn by the switch in this case, how would it look like with respect to the time? It would not be a constant DC, right? So you have a DC source, but the current will be pulsating DC, right? And maybe turn off completely when the switch is off. Whenever you turn on the switch, it is on off kind of thing. Is that correct? Because whenever this contact gets made, there is a current. Whenever it opens, there is no current. And this is, what is the frequency of this? This is 300 to 500. So the same frequency at which your speaker is oscillating. Is that okay? Right? So there are all sort of different types of load which are there on board, and they all run through this 12 volt battery. Now battery is a very in a way very nice person, because it does not crib too much. You are drawing this load, no problem, I would still maintain my voltage to be more or less at 12 volt. Of course, it is not exactly 12, it varies between, let's say, 12 to 14, but more or less it maintains the voltage and your sort of vehicle works, right. Question is, why are we talking about here? We are talking about this topic here is because there is a DC to DC circuit involved in this. Where is the DC to DC? Can anyone see? The DC to DC comes into picture not in this case, but in the case we talk about. So this is an, let's say, an ICE system. If we talk about EVs, you have a DC to DC in picture. Why is that? Because in electric vehicles, you would usually either not have this 12 volt battery, or you would not have the engine which is effectively powering up this 12 volt battery, right. So either you don't have engine, of course, or sometimes there is not even this 12 volt battery, right. So you have, in two wheelers you would usually have 48 volt batteries, right. If you are talking about four wheelers, you would have 400 volt batteries. Now the question is, you don't have 12 volt battery, but you still have a battery on board. Now if you want to run this horn, you want to run the lights, you want to run the infotainment system, sensors, everything, can you run it using these voltages? Let's say if you talk about two wheeler, this is electric two wheeler, this is electric four wheeler, right. Let's just for the timing, let's focus on two-wheeler. So you have 48 volt on a scooter, electric scooter. Can you use that 48 volt to run your speaker, horn? Can you use that? Because you no longer have this 12 volt battery on scooters, right? You only have this 48 volt battery now. Yeah. And has anyone sort of used an electric scooter? How many of you have used an electric scooter? Okay. Does it have a horn? Doesn't have a horn? Does it have a horn? It has a horn, right? So how does it work? Any guess? So now instead of 12 volt battery, I have a 48 volt battery, right? Which I charge whenever, I charge it whenever I take it scooter to my home or wherever. Now from here, how do I connect to that horn? Because this I was supplying through a 12 volt system. Now I have a 48 volt. What can I do? Got it right. How many of you say DC to DC buck converter? Okay, that is one option, of course. So you can use a DC to DC buck converter, right? Convert this 48 volt into 12 volt, and then you can supply this 12 volt to the same system, and your horn will work fine, or everything else would work fine. Any other suggestion? Any other suggestion? Then you will get, you can do that. That's a fair suggestion. You can convert it into AC using a transformer and directly use that AC itself to, supply to this, so you can get rid of this kind of a mechanism and so on. You can do, yeah. What else? Any other option here? If you don't want to use converter, voltage divider you can use. Yeah, but we have learned, right, that if at all you have to convert the voltage, better not to do using voltage divider, right? That we have already seen. What could be the simplest way? Simplest way is, you have, let's say, n turns here, right, which is producing some flux. You change the number of turns so that this can work with 48 volt. Simple. Isn't that the simplest way? You have an electromagnet, right? You have a coil wound around a piece of, let's say, magnetic material. You just change the number of turns so that the effective force with which the attraction happens remains the same, right? Isn't that the simplest way? Buck converter though we are learning now, right? We don't even know before, let's say, this class there is a buck converter. If you would have told you how to do it, you can just change the number of turns here, everything else remains the same. Tada, you have a new horn, isn't it? Which can work on 48 volt then. Is that correct? But then that is not how things happen in reality. That is how, as an engineer, I would probably think it this way, that it's much simpler just to change the number of turns and don't do anything else. But that's not how things work, because not just the horn, there are so many other systems, right? Each system you have to make changes. So whatever changes you make, that has to go to the manufacturing setup of those horns and things. You should have sufficient volume of these 48 volt based horns, otherwise manufacturing those may not be cost economic, right? So a system which is set in, right, which is this 12 volt system for automotive, makes all of these components enormously cheap and reliable. You want to shift to a 48 volt system in the vehicle where your horn, your light, your fan, everything works on 48 volt. It's not an engineering challenge, right? You can do it. As an engineer, we can design it, we can make it, but the challenge is making it cost effective, right? You have to gain sufficient volumes. All the vehicles should shift to 48 volt. Only one manufacturer shift to 48 volt. The person may not be able to source a reasonably cost horns of 48 volt and so on. So there are a lot of non-technical challenges in actually shifting the voltage levels. If you have heard about, for example, Tesla Cybertruck, right? This uses a 48 volt system, if I am not wrong, but you should try and go back and Google, right? So Tesla Cybertruck, all of you know what is a Tesla Cybertruck? How many of you know what is a Tesla Cybertruck? Okay, so those of you who don't know, go back and just search Tesla Cybertruck and you would know. So this guy on this vehicle you are using 48 volt bus instead of 12 volt bus for these horns and lights. But it is not a very common practice. Common practice is to use a DC to DC converter, generate a 12 volt and then run all the systems in the vehicle as it is. Any electric scooter if you pick up today, at least in India, this is how it would be, right? Nothing special, because so that everything else remains as it is, you just add this one component and you are sort of set up to run the whole vehicle. So this converter, what is used in the vehicles is mostly is a DC to DC buck converter. Okay, any doubts so far? There are challenges in that also. Your cost will go up. Finally, if you see everything gets driven, cost is a major driving force, right? So cost goes up, you have to do tapping at different values, you have to do balancing of those major block of batteries, so a lot of other issues may come up, but of course it's possible, it's not impossible. Okay, so now the question is, if you can use a buck converter to run all of these things, how does it practically work? So you have a 48 volt system and sorry, you are drawing buck converter. And then you have these loads. Now since this is a sort of a first course, most of the time the load we represent using a resistance, right? But in reality this is the load, right? You cannot represent it using a resistance because it's actually a non-linear load, right? It's turning on, off, this is the kind of the current it is drawing. But since it's the first course, you are learning about first time buck converter, so we can consider the load to be a resistive load, which means we are just considering the average part of this load, right? Somehow we are thinking that there may be some circuit inside which takes care of the ripple part, so we are only supplying the average power. So this is 48, you want 12 volt output, right? This is inductor, this is capacitor. What should be the duty cycle? What should be the duty cycle for the switch S1? 0.25, right, which is nothing but T on of S1 upon total Ts, which is nothing but VO by Vin, right? Alright, then the next question is, I can draw the waveforms. When S1 is on, now let us try to draw almost based on D equal to 0.25 so that you get a better picture. So this is 1, 2, 3, 4. And this is your Ts, this is your D times Ts, this is your S1 on, and in this period your S2 is on, right, because S1 is off. If I draw the inductor current IL, so what will be the inductor current? The inductor current would be going up and then coming down, and the initial and the final points are the same because we are considering the circuit is in a steady state condition, right, and therefore the initial point and the final points are the same. Alright. If this is inductor current, we saw that you can write an expression for delta IL. What was the expression for delta IL? Can someone recall? We did derive it in the last class. Okay, one of you. 1 minus D into into V in into Ts upon L. If this is delta IL, then this is the capital IL, which is nothing but the average current, right? This is capital IL, which is nothing but the average current, right? What is the average value? The min value plus max value divided by 2, that is the average of a triangle. And therefore, now if I have to draw capacitor current, right? What would be capacitor current? So, capacitor current IC would be given by IL minus IR, right? IC would be given by IL minus IR. Since this voltage is almost constant, IR is almost constant, and last time we saw that the average current in the capacitor is 0. So, therefore, the average of current in this resistance is equal to the average of current coming from the inductor. So, I can write this as small IL minus capital IL, which means the capacitor current is the inductor current minus the average value of the inductor current, right? That means all the ripple component in the inductor is what is going to go in the capacitor. Is this last equation okay? Any doubt? Any question? Okay. So, if I start at t equal to 0, right, you see if I subtract blue minus the yellow, blue minus yellow, it would be little bit negative, right. This is the place where I will have the 0 crossing, that means 0 crossing means where the current is 0, because blue is equal to yellow, and then it will rise further up, and again this is a point where I will have another 0 crossing, and it will further go down and to similar value. Right? That is how the capacitor current would look like. Is that okay? Any doubt? Yeah, of course this point and this point is the same. This is almost straight line. We have assumed all the components to be ideal, so all these slopes are almost straight line slopes, right? No saturation, no resistance in series. What is this point? This is nothing but IL max minus capital IL, right? Where what is IL max? IL max is nothing but equal to capital IL plus delta IL by 2, right? Similarly, you know the minimum point also. So, you know these points, you know all the x-axis points. This point where the capacitor current is at peak is D times Ts. Where the capacitor current is crossing 0, that point is, what is that point in time? What is time here? What is the time at which the capacitor current is crossing 0? This point, right? If you see that the top is delta L by 2, the denominator is, the bottom is also delta L by 2, so that these two are equal, the slope is equal. So, the time is also must be equal of these two sections. So, this is delta I by 2, this is dts by 2, this is dts by 2. So, therefore, the 0 crossing happens at dts by 2. Is that okay? Not okay? Similarly, this another 0 crossing point, what is this point? What is t at this instant? What is t at this instant? So, again, you know, this part is same as this part, although it does not look like that way, I have drawn it little bit, but it is, this part is equal to this part because this is average line from the middle, slope is the same, so therefore this is equal to this. So, if this total is 1 minus d times Ts, each of them is 1 minus d times Ts by 2. So, therefore time at this instance will be equal to d times Ts, which is up to this point, plus 1 minus d times Ts by 2. So, if you add this, what will you get? 1 plus d times Ts by 2, is that correct? Yeah. Which one? Second part, it's straight line, right? Slope is the same. So x by y ratios on both sides would be same. So this side, if you see, this is delta I by 2, this is delta I by 2, and therefore this period is same as this period. This total period is 1 minus d times Ts, and therefore half of them is 1 minus d times Ts by 2. So time at this instant is 0 plus dTs plus 1 minus d times Ts by 2. Okay, once we have figured out the capacitor current, the next step is to find out the voltage, and this is again what we have drawn last time, but let us still try to redraw it. Capacitor voltage, and now we are drawing the zoomed version of it, right, on the y axis. So whenever the current is in the capacitor is positive, capacitor equation is I equal to C dVc by dt. So if current is positive, dV by dt will be positive, current is negative, dV by dt will be negative. In this region, the first region, the current is negative, so that means voltage is falling, and then the current is positive, that means the voltage is rising, and then again the current is negative, so the voltage is again falling, coming back to the same position because it's a sinusoidal steady state. This is how VC would look like. Is that okay? Anyone has any doubt? Sorry? Is the integral of IC correct? No, if the current is negative, the voltage will not be negative. The derivative voltage is negative, right? So that means the slope of voltage is negative. The voltage itself need not be negative. It could be not, right? But what we know from this equation is definitely the slope is negative. You don't know the C, right? Plus C. If you do an integral plus C, right? So this is the C. So the C is actually very large enough. We have drawn a zoomed version of it. Any question? No question? Yes. This one, why is it at half time? Okay. Draw it on this side, and then we can see it a little bit more carefully. This is I max, this is I min, and this is the average line, which is I max plus I min by 2, right. This instant is d times Ts, this instant starting from t equal to 0 is Ts, right. Now the question is, what is T1, let us say, right, this is what we want to find, what is T1. So assume this guy has a slope m, right. So y upon x is m, so m is nothing but equal to y, which is I max minus the average value, which is I max plus I min upon 2, right. This is this y axis divided by the x axis, which is T1 minus d times Ts, right, and this is same as slope. So this is same as what we have on the right side, which is I max plus I min by 2 minus I min upon Ts minus T1, right. So if you solve it, you would get the same answer. Okay. Okay, then can you do one thing, since now you know how you got this waveform, can you try to find delta Vc. Before you find the expression, let me tell you why finding delta Vc is important. Because there is our, we erased it. There was a 48 volt battery, there was a DC to DC converter, and that is what was going into a horn, light, fans and so on, right. Imagine this guy has an output voltage ripple of 5 volt. So you have 12 volt, but output is oscillating 5 volt, right. So what will happen is this would create problems with your loads, right. So let us say fan load, right. So now the fan load would have this oscillatory torque and it would make sure that the fan degrades much faster. Similarly electronics, right, electronics may not accept this kind of a highly variable power supply. So all these loads would expect a very nice clean power supply. Now when we say clean or when we say nice power supply, how do you quantify it? You quantify it in terms of ripple. So let us say the audio system manufacturer would say like, look, you can power it with 12 volt supply, but the ripple in the 12 volt must be less than 1%, right, 1% of 12 volt, that means how much? 0.12 volt, right. So this delta Vc should be less than 0.12 volt, and therefore when we understand these circuits, when we use this circuit, it becomes very important to find out this delta Vc and how this delta Vc depends on different circuit parameters, so that we can tune those and we can bring the ripple within 1%, which is required by the load. So can you go ahead and find the expression for this delta Vc? Use this basic equation, try to find from which point to which point you need to integrate it, and I think that is it. It would not take much effort after that to get the expression. Anyone, any guess? So she is asking that whether value of Vc at t equal to 0 and t equal to Ts, would it be same? Yes? Why? Why would it be same? Bol bhai. Sorry? Steady state, na? So assumption is steady state. So go ahead, can you guys solve for delta Vc now? Solve for delta Vc by integrating I equal to C dV by dt. So I is equal to C dVc by dt, right. You can take IC dt is equal to C times dVc and you can integrate on both sides. The objective is to get the ripple, right, and you would get the ripple if you subtract this maximum Vc with minimum Vc, right. So you want to have the ripple on the right side eventually, so you put Vc min and Vc max as the limit. Now what is the time at Vc min? The time at Vc min is nothing but dTs by 2, and the time at Vc max is 1 plus d times Ts by 2, right. Now you just need to integrate it. The only challenge, little bit of step here is C is of course a constant. So therefore integral of C dt becomes very straightforward, right. On the left side you have an integral of IC dt. IC is not a constant, right. IC is actually changing. So when you integrate from this point to this point, right, you have to find the area under this small triangle, right. You have to find area under this triangle, which you can find because you already know what is the Imax, right. You know the Imax, you know delta I, so you can find the expression for delta Vc. Can anyone find out what is delta Vc? Okay, how many of you have found what is delta Vc? Oh, lot of you. Okay, great. So, tu bata. Delta IL times Ts by 8. Is that correct? Is that correct? Okay, and let us also substitute delta L, right, just for looking at the big picture. 1 minus d times V in times Ts squared upon 8 LC I don't remember it, so if anyone thinks it's not correct, let me know. So if your ripple is 2% and you want to bring it to 1%, what should you do? If you have designed this converter and now you are going to a electric two-wheeler manufacturer and you are trying to sell this buck converter to them, and this guy tests it, sees the ripple as 2%, says I'm not happy with 2%, make it 1%, then I can buy it. So what will you do? What will you change in your converter? So what will you change? C value you can change. What else? L. What else? TS. What else? What else? D. What else? Yeah, so you cannot change D, right? Because if you change D, then the output input voltages will also change. That you don't want. So D is ruled out. So you have options of C, L and TS. Yeah, of course. So D you have to maintain constant. You can change TS if you want. Will you increase TS or reduce TS? Reduce TS. That means you will increase the FS, which is the switching frequency, right? If you have to increase Fs, what is the implication of that? Switching losses will go up because now you are switching more frequently, right? Higher Fs means number of cycles per second. So you are switching more frequently, switching losses will go up. So maybe you would do that if you are happy with the efficiency, you are okay in reducing the efficiency a little bit, but you don't want the size to become more, then you would increase Fs. But if you are very finicky about efficiency, you cannot afford the efficiency to reduce, but you are okay in making it a little bit bigger, then either you would change the value of C or you would change the value of L, or you would change the value of both depending on the cost of those components, size of those components and so on, right. So the implication here is on size and the implication here is on the efficiency. Yeah, you can do that. You can try to find a different capacitor which gives you more capacitance with the same size. Of course, it will be expensive, so there is always a trade-off. But you can do that. You can look for some different types of capacitors as well. Now tell me one thing. If now you have designed it as per the spec, right? This guy wanted 1%, got it to 1%. You have given it to the vehicle manufacturer. Let's say vehicle manufacturer puts this in the vehicle and turns on the horn. Now will your output voltage ripple still be 1%? So if you designed it with some R load, but in reality the load is the horn which we have seen, and now you connect the actual load, will your ripple still be 1%? Yes? No? No, right? Will it be more than 1%? Yes? No? Let's only look at the capacitor part, right? Forget about the buck converter. Think of the inductor as one current source and the load. Oh, how do you represent load? This is inductor, this is load, okay, L load, AD load, fine. So you have IL which is inductor, I load which is load current. So just think of this as a zoomed version of this outside, this picture. So IC is equals to IL minus I load. Now IL is the same what it is. So IL has a average component which is I am representing, let's say, using capital IL, and it has a ripple component which I am writing as delta IL as a function of time, right. This is the ripple component, this is the average component, correct. Similarly, load also I can write it as the combination of these two components, which is the average load current plus the ripple load current, alright. At steady state, capacitor will not draw any average current, and therefore this average current must be equal to this average current, right, because the average capacitor current is equal to 0, and therefore these two terms must match and cancel out. These two terms must match and cancel out. If we had resistance only, then there was no this term, right, this was 0 anyways. So capacitor current would only be equal to this, and you have calculated delta V based on this. But if you also have a load which has a oscillating current, then this current will get subtracted from this current, right, and the net current would flow from the capacitor. So the ripple from this guy plus the ripple from this guy both will flow through the capacitor, right. If it's a nice coincidence, which is never going to happen in real life, that this guy becomes actually negative of this, or the load current is negative of this, then they may cancel out and your ripple may reduce. But that would never happen. Why would that happen? You have designed your converter to operate at 10 kilohertz, horn is operating at 500 hertz. It's very unlikely that these two guys can cancel, right? They are not even of the same frequency. So therefore, most of the time this would add further ripple on the capacitor. And now you have to size the capacitor so that even with this kind of load, your ripple is 1%. Is that okay? Is that fine? So this extra horn would actually increase your burden on the output capacitor. Any question? Any doubt? How is? Because now you have the capacitor current is combination of this delta IL and delta IL I load, right? Earlier this term was not there, there was only one term. So now you have to make sure with both the terms together, the ripple should be within 1%, yeah, and they would not cancel each other out. I mean, of course, if they would have cancelled, then it would have helped, but they would very unlikely or almost very small probability they would cancel. So it would end up increasing the pressure on the capacitor in terms of more ripple. You can of course do the calculation if you want, it's not very difficult. Once you have done this calculation, right, the same process you can use to even calculate what will be the ripple because of the load current. If I give you a load current, shape and so on, you can calculate the ripple here also, but let us not do that now, but you can. So I can ask it in the quiz, in the assignment. Okay, any questions so far? Load ripple is let us say a sinusoid of time. Now what do you mean by negative, positive? It's a sinusoid with time, right? Or it's a square wave with time. So any doubt? Analog, any doubt? Analog 1, analog 2, any doubt? So next question is that how do you get these S1 and S2, right? Because so far we have only drawn them as switches. These are not mechanical switches, these are semiconductor switches, right? So in reality these are essentially combination of MOSFET and a diode. So you can put a MOSFET here, gate, source, drain, this is switch S1, this is diode D, this is anode, this is cathode, right. This is one realization, as we call it, of that circuit where you are using one MOSFET and a diode. You could have realized the same circuit by using two MOSFETs also, you could have realized the same circuit using two MOSFET plus two diode also, you could have done a lot of things. This is one realization which is the popular one. So as far as this class is concerned, let us sort of look at this particular realization and how it works. When this MOSFET is on, this channel is created, so this becomes a short circuit here. As soon as this becomes a short circuit here, the positive voltage gets applied across this terminal, this becomes positive, this becomes negative, diode is turned off. So therefore that condition that whenever switch is on, S1 is on, S2 must be off, that is sort of getting automatically satisfied. Is that okay? Whenever S1 is on, this voltage appears here, the diode becomes reverse bias. Whenever the switch MOSFET is off, this channel is off, the inductor still requires a path for the current to flow through, and this we have discussed in the previous lecture. It cannot flow through this channel because it is off, so it flows through this diode. So automatically when this turns off, this guy turns on, right. So this somehow meets our requirement of S1 and S2. Is that okay? This circuit you have seen before, right, in 103? 103 you have seen this circuit? Okay. You could have done more, you could have, instead of using this diode, you could have said that I use one MOSFET here also, which is also possible, and we will look into that little bit later, but this is like the most simplest way of implementing a buck converter. Use a MOSFET, use a diode. What happened? What is A? A is anode, D? K is cathode. Yeah. Want to write C, but C is here, so let's write K. Any question? Yeah. What forces the diode to be turned on when the MOSFET is off? So when the MOSFET is on, the inductor current would rise, right, as it does here. And now when you turn off the switch, there is a positive inductor current, and then what? And that current will force that diode to turn on. Why would that happen? Because if the diode does not conduct, then the voltage across diode would be infinite in the forward bias, and therefore it would actually not reach infinite ever, but it would in a way turn on the diode, ending up turning on the diode. So as soon as this switch is off, this inductor will flow through this diode. This is something which we discussed in first class. Do you guys remember anyone? Anyone remembers that? No? So we were discussing, right, the diode gets, this was my question, the diode gets turned on because of voltage or current, right. Usually we say, positive voltage it will turn on, positive voltage will turn on, but here we are saying because of the current, because this current doesn't have any path, it will turn on, but that's like ridiculous. How would diode know that there is no path for the current, right? So how diode knows is because imagine if this diode does not turn on, right, this inductor current will become suddenly 0, so diaverity would be infinite, and it would force a polarity of voltage like this on the diode, and that means the diode will turn on, right. This condition would never happen that there is an infinite current. So if there is a diode in this fashion, it would turn on, and it would lead the continuity of the current which is flowing from the inductor. Yes, because the inductor current, if it has to be abruptly stopped, it would lead to a very high voltage, and which can easily turn on the diode. So in reality it would never get interrupted, and it would never lead to a very high voltage, and the diode would just turn on as soon as the switch turns off, to make sure that there is a path for the inductor current to flow. Is that okay? Not okay? Same case, D equal to 1 by 4. This is the inductor current, and this is the average value of the inductor current. The circuit is operational, right? Perfectly working fine. Your vehicle, let's say lights are on. lights are, you can sort of model it as more or less resistive or rather a continuous current. So, there is a continuous current which is flowing in the load and your converter is working fine. What if the load resistance increases? That means you turn off the light, right? Of course, it would in reality be a step change. So, lights are on, lights are not on, right? But here let us consider it as a more continuous sort of problem. So, we are gradually, let us say, increasing the load resistance slowly. That means we are reducing the load current slowly. What will happen to this circuit? What will change in this circuit? So, the problem we are talking about now is what would happen if RL increases. That means RL increases means light load condition, right? The load is reducing. The current flowing in this, which is I load, in this case this is almost constant, which is capital I load will reduce. Is that correct? Capital I load will reduce. If capital I load reduces, will this current change? This current will also change because capital I load is nothing but equal to the average of the inductor current, and therefore if this average current reduces, this average current also has to reduce. So what will happen? Your inductor current average will shift down with a new value of average. Let me call it IL1. Everything has shifted down. Does the output voltage also change? The output voltage expression, the output voltage, you remember the expression, right? Will that also change? No, because that was V out by V in is D, we are maintaining the same D, so it remains the same. Is that okay? So going from R0 to R1, your IL reduces, your VO remains more or less constant. Is this part okay? Not okay? Anyone wants me to repeat this part? Which part? Go ahead, which part should I repeat? Okay, so the average load current changes, right? The average load current changes, that means the average current coming from the inductor also changes, right? And which is what we have drawn in this new yellow line, right? The output voltage remains the same. Let us say I further reduce RL and take it to R2. Just starting from 0, it's ending at 0, just touching 0. This is the average component, IL2. Load current average will reduce, inductor current average will reduce. Still my output voltage would remain constant. Why? Because still for this region you have a positive voltage across the inductor V in minus V0. For this region you have a negative voltage across the inductor minus V0. And if you apply the volt second balance, you would still get V0 by V in is equal to duty cycle. So still the voltage relationship remains valid, your duty cycle is constant. I am increasing the resistance. So increasing resistance or reducing the load? Yeah. Increasing the resistance or reducing load, they are one and the same thing. No, increasing resistance is reducing load. When we say we reduce load, that means we reduce the load current, right? So that's a general nomenclature. When we say we reduce the load power or the load current. right? That means we are increasing the resistance. This we have been following in transformers also, right? When we say we reduce the load, that means the kV of the transformer outload comes down and therefore the current comes down, right? So the impedance actually goes up, or the resistance or the inductor values will go up. So far so good. Any doubt till R2? Now let's take a big jump from here and go to R3. Yeah, really large value. The average current has to be really small. Use a different color here. Or rather, let me draw it separately now, not in the same graph. We will slowly analyze it, but for now, and this will continue, of course. Right? If the load current further reduces, that means the average current has to further come down. This is what would happen. When the switch is on, the current would rise, right, through the inductor. The voltage across inductor is positive. When the switch is off, diode will start conducting, the negative voltage will appear, the current will start falling, and current will come to a point where it will become 0. And beyond which, ideally, if this would have been really a short circuit, the current would have started flowing other way around, because this is a positive, this is a voltage here, right? This is current has become 0, so now it will start flowing in the reverse direction. If this would have been an ideal switch or a perfect short, but because this is a diode, it would not allow the current to flow in the back direction. So after this instant, nothing will happen. So your circuit will just remain here unless the next time again you turn on the switch and then again current will start rising. So this is how the waveform would look like if you increase the resistance to a very, very large value. Roughly, right? We will quantify the slope, we will write the equations, everything, but roughly this is how the waveform would look like. Any other doubt? So what she is saying is how would, let me sort of explain this part again. So this switch is on, right? S is on. What is the voltage across inductor? Voltage across inductor is Vin minus Vo, positive. So the current slope is positive, current is rising, all okay. I turn off this switch, the current slope becomes negative, VL becomes equal to minus V0, slope becomes negative, current starts falling, current is still in this direction but now falling. At one point current becomes equal to 0, let me call it as some T alpha. At T alpha current becomes equal to 0. After this, the current will have a tendency to start flowing back again, because this is a voltage, let us say this is 12 volt, there is an inductor here. If this is a short circuit, the current will start flowing in the negative direction, but because this is a diode, it would not allow to do that. So therefore there is no other option but the current would remain at 0 till again in the next cycle your switch turns on. Is that okay? If we would not have used the diode, if you had used the same circuit here, what would happen? The current would have started flowing in the negative direction. But this is not a real circuit for now, so let us now first look at the diode. So diode will stop conducting, will not allow the current to flow through in the negative direction. No, so this is how the inductor current would look like. It will not go negative, it will never go negative. It will only remain positive. What difference in the? Yeah, because this diode cannot allow negative current, right? As simple as that. If you had an ideal switch, current can be positive, current can be negative, anything is fine. Diode would never allow a current to go in the negative direction. Yeah, that would allow, of course. So instead of diode, if you use MOSFET, then things would have looked a little bit different. We'll look into it also, we'll look into that case also a little bit later. But for now, consider that it's a diode and because it is a diode, the current will not go negative and then it will clamp just to 0. We will come to that, we will come to the slope, we will do the calculation, we will come to that. Graph would still start from origin because the current is 0. First time you turn on the switch, the current will start from 0. If again it comes back to 0, it remains 0 for some time. Next time you turn it on, again it will start from 0. The slopes will change and we will come to that. We will do the derivation soon. But what I am trying to say is this is how roughly it would look like, right? What is the exact value of slope? All those things we will write equations, don't worry. So this is an important mode of operation as we call it, because it is a very practical scenario. You use a DC-DC converter, the load is very light, let us say there is only light on, nothing else is on, or only there is an audio system which is on, nothing is on. The converter is operating at a very light load condition, and this is the kind of waveform which would be there in that case. So there are names of these conditions. What are those? What are the names? Right, we call it CCM or DCM. CCM stands for continuous conduction mode, which was the case with R0, R1. Case R3 is where the current comes to 0 and it remains at 0 for some time. We call it discontinuous conduction mode. So discontinuous conduction mode means the current should touch 0 and should remain at 0 for some finite duration. We start calling it discontinuous conduction mode. So IL is 0 for finite time. This is the condition for discontinuous conduction mode, or rather if that happens, we'll name it and we'll call it DCM. The first case where the current is continuous, it means it's never remaining at 0 for a finite duration, we are calling it continuous conduction mode. This case, which is R2 case, which is like it's touching 0 and then it's again going up, it's touching 0 again going up, it doesn't remain 0 for a finite duration, so it's not a DCM, still touches 0, so it's not necessarily a CCM also, it's somewhere in between, we call it critical conduction mode. It's somewhere in the middle between the two, this is like a boundary of the two cases, right. Don't use the acronym CCM for this one also, we'll use CCM for this, we'll use DCM for this one we have to take the full name, critical conduction mode. This IL is DCM, these top ILs are CCM, and this IL2 is in critical conduction mode. Okay, so now what we'll do is next time we'll try to write formulas for these, we'll try to do some little bit of derivation, conditions and all those things, and we'll also solve the quiz paper in the class.